Hello everyone, welcome again to Discrete Mathematics with me, Adila Krishnadi. Um, Here, we talk about the notion of adjacency and incidence. Um, when we have a directed edge E here with source U and target phi, then we will say that U is connected to phi, and also phi is connected from U by the edge E. So by the edge E. Sometimes sometimes we simply write the edge E as the pair U comma phi, if we don't really care the name, right? In particular, if E is not parallel to another edge. Uh, Similarly, we will say phi is adjacent to U, but not vice versa. So adjacency is not symmetric in directed graph. So if I draw this here, this is the directed edge, this is U, this is phi, this is E. Then we say that U is connected to phi by E, phi is connected to U, phi is connected from U by E, and also phi is adjacent to U. So phi is adjacent to U, but not vice versa. Yeah. Now in undirected graph, however, we have slightly different situation. If you have an edge E connecting uh, U and phi, then we say that U and phi are connected by E. U and phi are connected by E. And we simply sometimes write E as the set of pairs, the set of containing two nodes U and phi, if that edge is not parallel to another edge. And also in this case, we will say that U and phi are adjacent. U is adjacent to phi and phi is adjacent to U. So U and phi are adjacent. In undirected graphs, adjacency is symmetric. Remember, in directed graph, adjacency is not symmetric, whereas in undirected graphs, adjacency is symmetric. Now, uh, if you have these connections or this, then we will say that E, the HE, is incident to both U and phi. So is incident at U and at phi. Yeah. Excuse me. And the nodes of U and phi are incident to the edge. So incidence is a closely related notion. So if phi is adjacent to U, then there must be an edge incident to both of these nodes. Now, from the idea or the notion of adjacency and incidence, we could define a notion of neighborhood. So given a node U, yeah, then the neighborhood of U is the set of all nodes adjacent to U. So set of phi that is adjacent to U. So neighborhood of U is all nodes adjacent to U, which may include U itself, right? If you have a loop, right? Now, a proper neighborhood of U is simply neighborhood of U, but you take out U if U is there, right? So the proper neighborhood is really other nodes. There are neighbors to U. Now, then you could, so for example, here is U, this is V, this is W, then, and you have this, yeah, then therefore the neighborhood of U is U, phi, and W. Say, and the neighborhood of phi is U and W, so its neighbor of W is U and phi. Right, but if we have direction, then you have to take into account the directions. So And then you could then define a neighborhood of a set of nodes. So that is a neighborhood of the set of U, capital U, is the set of uh, all neighbors of the uh, nodes in U. Yes, all neighbors of some nodes in U. And the proper neighborhood is really just you make sure that the set does not contain nodes in U. So to clarify this, let's see some examples. So here's an example, our graph earlier, right? So what will be the neighborhood of A and neighborhood, proper neighborhood of A, and then neighborhood of B. Sorry, not this one. I should write it as a set B and D, and then the proper neighborhood of B and D. Now, neighborhood of A is really just A because of E1, and then B because of E2 and E3, and then C because of, well, E4. Proper neighborhood of A then is then consists of B and C. All right, you take out A out of it. How about the neighborhood of the set B and D? So you take all the possible neighborhood. So what will be the neighborhood of B? Will be A and D, and then the neighborhood of D is of course D itself. D is there, and B, and then C, right? Because D has B as a neighbor and has C as a neighbor, right? Now, how about the proper neighborhood of this set? Yeah, here. Then you take out B and D, so you just have A and C. Yeah, so these are the neighborhood. Now, how about the case of directed graphs? Here is the case of directed graphs. The neighborhood of A is, well, just B. Remember, adjacent to A, the node adjacent to A is only B here, but E is not adjacent to A. Yeah, and the proper neighborhood of A is also the set containing just B. How about the neighborhood of C? Neighborhood of C would contain, well, C itself because of the edge E3, and then B because of the edge E2, and then D because of the edge E4. And the proper neighborhood of C would then be B and D. Yeah. And finally, the neighborhood of the set B comma D. So what will be the neighborhood of B? Then you have E. So because you could go to E, because E is adjacent to B. Yeah. And the neighborhood of D is C. Yeah. Okay. And of course, the proper neighborhood of B and D is also containing just C and E. Yeah. So that's a definition of the proper neighborhood and neighborhood for directed graphs. So let's now do this in exercise. We use the same graph, innovation provinces, as well as the bit strings of length 2 that we saw earlier in the earlier videos. Try solve this exercise. Try solving this exercise first before we discuss the solution in the next video.